Hello, classes. Let's do another review for this final exam, and we're going to do some more of the logarithms and the exponentials, and then we'll have more review later on, which will cover the other sections. And this is college algebra. Okay, let's start off with this thing here. Solve the following exponential equations. So we've got 9 to the x equals 27. So 27 is not a power of 9, but we can be crafty. Isn't 9 and 27 both a power of 3? So that's what I jumped on. If you didn't think of that idea, you'd have to use logarithms. But it's easier if you don't have to use logarithms by being crafty. So let's call 9 3 squared to the x equals 3 cubed. So notice this and this are equivalent equations. And then let's try to simplify matters. So 3 squared to the x power, isn't that a power to a power? So what do you do in that case? You multiply the exponents, so that becomes 3 to the 2x equals 3 cubed. So notice that accomplishes a lot. We made it more compact. From here, we weren't ready to do anything real snazzy. We have to make it more compact. So that's what we did. We took advantage of the rule of exponents. Power to a power, you multiply the exponents. So we have this. Now it's compact like a Volkswagen, and we're in that special place. The bases are the same. They're equal to each other, so therefore the exponents have to be the same. So be bold and set the exponents equal to each other. And now we have a linear equation, and then solve for x and divide both sides by 2, and you get this answer. Let's move on to the next problem. Again, an exponential equation. I see a variable in the exponent, I see the equal sign, so it's an exponential equation. So I'm thinking right off the bat, how do you solve exponential equations? Well, you can get lucky like we did here by rewriting the bases, or in this case, we can't write 5 as a power of e. So think logarithms. Logarithms unlock the exponent. So I'm going to take the ln of both sides, and that's a great property of logs. It's this property. If you have a equals b, if that's true, then this is also going to be true for sure. You can turn each side of this equal sign into an argument of a log with the same base, a and a I did. So if this is true, then that's going to be true. And that's a nice property. It's kind of obvious, but it comes in handy because, okay, so we did that to get to here. And now let's use another log property. Isn't this ln, isn't the argument an exponential? And isn't the same base, e, and that's really log base e. So this is composing inverse functions. And whenever you compose inverse functions, it always means this. The initial input will equal the final output. So that's what we did, that log property. So we just get negative 2x equals to ln of 5, divide both sides by negative 2, and we get that answer. Okay, let's try the next problem. Find the inverse of this. So whenever you're asked to find the inverse of a function, think of the 3 steps. Change f of x to y. Step 2, interchange x and y. And step 3, the hardest step, solve for y. So let's do step 1, change f of x to y. So we have this. I wrote ln as log base e, and that's the argument x plus 1. I like to see the base there. It makes it easier. Okay, so we did step 1. We changed f of x to y. Step 2, interchange x's and y's. So that's why I wrote x equals log base e of y plus 1. And now step 3, solve for y. It looks tough. How do we solve for that y? How do you, well, identify what you're looking at. It's a log equation. And what's the best way to solve a log equation? To bebop to its equivalent exponential form. So what's my base going to be in exponential form? The same as that base in a log, e. Logs are equal to the exponents. So that's where the exponent goes in exponential form. Then equals whatever's left, the argument. And now, one more step to go, subtract 1 from both sides. So you get e to the x minus 1 equals y. And really that y is really f inverse. Okay, next problem. write this expression as the logarithm of a single quantity. So notice this expression has 3 terms in it. Terms are separated by pluses and minuses. So we want to write this as a single log. So this is 3 terms. This is a tough one. When it's got more than 2 terms, it's a little tougher. Just do it in order, in the order that you see it. So first thing I want to do is make it more compact before I do anything. So let's change that coefficient into an exponent on the argument. That's a property of logs. Same with this one here. A coefficient, make it into an exponent on the argument. So that's what I did here with the first step. And now the second step. Let's look at only the first 2 terms. We're adding logs with the same base. They both have base e. So let's write it as a single log. So I'm going to write down ln, and then what am I going to do with these arguments? Multiply them, since we're adding those logs. And then let's rewrite that third term over here. And now let's do the same thing. Let's write it as a single log. We know how to write this as a single log. When we're subtracting logs, you write as a single log and you divide the arguments. So this argument over that argument. And that problem's done. And let's look at this problem here. This is just a straightforward log equation. How do you solve for x here? How do you solve for that x? So notice you got to be on your toes. There's no log on this right-hand side, so I'm not going to like drop logs or... So how do you solve a compact log equation? Bebop to its equivalent exponential form. So the base is 4, so that's 4. Logs are equal to the exponent. That's where the exponent goes, so then equals whatever's left, the argument. And now this looks straightforward to solve. We get 16 equals x plus 7, or x equals 9. Okay, let's move on to some more problems. How about, from a former test, determine the domains of the following functions using interval or set notation. So let's take a look at this log function. What's the domain of this log function? You don't even have to worry about the base. It's all about the argument. The argument of a log has to be positive. So just write the argument as an inequality. So it's x minus 3 is greater than 0. Always make that argument greater than 0, and then solve for x. Add 3 to both sides and you get your answer. That's the domain, or in interval notation, that's the same thing. What's the domain for this exponential function? You don't have to think about it. What's the domain of any exponential function? All real numbers, so you don't have to think about it. That's the beauty of exponential functions. The domain is always all real numbers. Let's take a look at this problem here. We're asked to sketch the graph of this log function right here. So it looks like only one transformation. A horizontal shift, 1 unit to the right. We want to state the domain and range of the final graph. So what's the basic graph that we can extract from this? Isn't it just going to be that y equals log x? Or notice the base is 10. If you don't see it, it's assumed to be 10. And then all basic log functions look like that. Looks like a small r. The word logarithm has an r in it. So that's a good way to remember. What do all basic log graphs look like? A small r. Notice x equals 0 is always the vertical asymptote for all basic log graphs, and this is always an x-intercept. And let's say I came up with more points here. Like if you let x equal 10, for instance, isn't the answer going to be 1 because of that log property? If the base equals the argument, the answer is always 1. Or what happens if the argument is 1? Isn't that a property of logs? If the argument is 1, the answer is 0. We plotted that point right there. And if you let x equal 1/10, that's a positive number. What is the output going to be? -1. Because isn't 10 to the -1 1/10? Okay, so there's the basic graph. Now let's do the final graph, doing that transformation. So right here. So all I'm going to do is, with that prior graph, move it 1 unit to the right. Notice a horizontal shift affects a vertical asymptote. It was x equals 0, the vertical asymptote, but we shift that vertical asymptote 1 unit to the right. We shift this graph 1 unit to the right, and we get this. And notice all the ordered pairs, all the x-coordinates get bumped up by 1. So the x-intercept, instead of being 1, 0, it's 2, 0, etc., etc. And what's the domain of this log function? Use your vertical asymptote. Remember, domain and vertical asymptote are super related. So that's why it's x is greater than 1 or 1 to infinity. What's the range? Range for any log function is always all real numbers. And the vertical asymptote is x equals 1. Okay. Let's see what else we have here. Some other goodies here. Let's try solve the following equation. So here we have an exponential equation. How are we going to solve that for x? Very important. We want to make this x term as bare bones as you can. Always, if you have a number there, a coefficient, get rid of it. Let's divide both sides by 3. And we get this equivalent equation. And now, I can't write 3 as a power of e, so we got to think logs. Let's use that property of logs again. If you have a equals b, that's the same thing as log a equals log b. So turn each side of this equal sign into an argument of a log with the same base, and I chose log base e. So ln of e to the 5x equals ln of 3. And then again, that property comes up when this is composing inverse functions. So the answer is just going to be the exponent. So 5x equals ln of 3. Divide both sides by 5, and you get that final answer. Let's do the next one. This is an exponential equation, and I notice 16 is a power of 4, so let's not even use logs. Let's write this equivalently as 4 to the x equals 16 to the negative 1. Isn't that the same thing as 1 over 16? Because what's 16 to the negative 1? 1 over 16. And let's write 16 now as a power of 4. So I have 4 to the x equals 4 squared to the negative 1 power. Let's next do this property of exponents, rule of exponents, a power to a power. You multiply the exponents. So now we have 4 to the x equals 4 to the negative 2. Isn't that looking a lot more compact now? And then we're in that special place, so set the bases are the same, they're equal to each other, so the exponents have to be the same. So x equals negative 2 is the final answer there. And then let's see, what about this one here? Ln of x equals negative 2. If you want, you can rewrite that as log base e of x equals negative 2. It's nice to see the base. Don't be afraid to do that. If you see ln, change it to log base e of x equals negative 2. So these are the exact same thing. And then how do you solve? We want to solve for the argument here. So let's convert it to its equivalent exponential form. The base is e, logs are equal to the exponent. That's where the exponent goes, equals whatever's left, the argument. And that problem's done. Sometimes we like to simplify negative exponents, so isn't e to the negative 2 the same thing as 1 over e squared equals x? So that problem's done. Here, notice here we got logs on both sides of the equal sign. About 4 minutes ago, we had a log, but not a log on the other side, so we had to be brought to its equivalent exponential form. But here, let's use that property of logs. It's this one here. If you have log of a equals log of b, you can just set the arguments equal to each other, a equals b. It's kind of like what the property I did a couple minutes ago in reverse order. So set the arguments equal to each other. Boy, that makes it a lot easier. It's just a linear equation, and we know how to solve for that, and you get that. Subtract x from both sides, etc., etc. Okay, and then what about this problem? We want to write this as a single logarithm. We've done a problem similar to this, I think, recently. Let's change that coefficient to an exponent on the argument. So we have that. Rewrite the second term. And now we're just adding two logs. So write it as a single log and multiply the argument. So that problem is done. Any others? I think that looks pretty good. So, carry on, everyone, and study hard for this final. Goodbye.